This discussion, we are going to prove the most beautiful equation in mathematics, which is the Euler's identity, which is it involves the combination of imaginary numbers, real numbers, and the value of e and 1 and 0. And before I start this discussion, I want to recommend you a channel which is here. And if you love the basic math which is involved in high school, so you can visit this channel. Okay, now let's start our discussion. In today's discussion, we are going to prove the most beautiful equation in mathematics, which is the Euler's identity. And to formally start our discussion, the first thing we need to do is to prove it first. This equation. I also create the equations that we are going to form while we are proving, and a separate page for proving. So, to start our discussion for today, let me give you this idea. We have f of x is equal to the summation of x raised to n over n factorial times f raised to n 0 as n start to 0 up to infinity, which is we all know as the Maclaurin series. So this is the function that we are going to use to prove. So the first function that we are going to compute is the eix or e raised to x. So based on Maclaurin series, since e raised to x is a continuous function, so we have this formula: x raised to 0 over 0 factorial times f function of 0 plus x raised to 1 over 1 factorial times first derivative of function 0 plus x raised to 2 over 2 factorial times second derivative of function raised to 0, and so on. So, as we substitute the value of function, so the function of x is also equal to e raised to x, and the first derivative is e raised to x also, and e raised to x the second derivative, and so on. Then substitute it as function of 0, which is e raised to 0 is equal to 1. So we get all values as equal to 1. So we get this pattern. So let's substitute it to our equation. So we get e raised to x, then 1, okay, x raised to 0 over 0 factorial is 1, times 1 is 1, plus x raised to 1 over 1 factorial is x. Then we get x squared over 2 plus x cubed over 6, and then x raised to 4, then 4 factorial is equal to 24. So that is for the function e raised to x, and so on. But we are looking for e raised to ix. So we are looking for e raised to ix. So let's substitute e raised to x as e raised to ix. So what we do here is just simply add I or multiply I on the equation. So we get 1 plus ix plus ix squared over 2 plus ix cubed, quantity ix cubed over 6 rather, plus quantity ix raised to 4 over 24. So let's recall the imaginary or I identity. So we all know that I is equal to square root of negative 1. Therefore, I squared is equal to square root of negative 1 squared. So we can cancel square root and the squared. So we get negative 1. And the value for I cube now is we have this square root of negative 1 times square root of negative 1 times square root of negative 1. So we can multiply square root of negative 1 and square root of negative 1, and we get negative 1 times square root of negative 1, which is, we all know that the square root of negative 1 is also equal to I, times negative 1, so we get negative I. Then I raised to 4 is also like I squared times I squared, and I squared is equal to negative 1 times negative 1 is 1. So we can simplify our function above. So we get e raised to ix is equal to 1 plus ix. Then it will become minus x squared over 2. Then I cube is negative I. So we get negative I x cube over 6. And I raised to 4 is equal to 1. So we get x raised to 4 over 24 plus and so on. So since it is a series, so there's a continuation. So the first equations we form is e raised to ix is equal to, just rewrite it again, 1 plus ix minus x squared, okay, minus x squared over 2. Then minus ix cube over 6 plus x raised to 4 over 24. So we have now the first equation. Now let's prove cosine x, or compute for the function cosine x. So like what we did, since cosine x is a continuous function, so we use the Maclaurin series. So x raised to 0 over 0 factorial times f raised to f function of 0 plus x raised to 1 over 1 factorial times first derivative of function, okay, 0 plus x squared over 2 factorial times second derivative of function 0. It should be 0, not 1. And so on. Since it is a series or a continuous function, we expect for other values. So the function here is cosine x. So the first derivative of cosine x is negative sine x. And the second derivative of the function is negative cosine x. The third derivative of function x is sine x. And the fourth derivative of the function x is cosine x. So now let's try the function of 0. So cosine 0 is equal to 1. And cosine, then negative sine 0 is 0. Then negative cosine 0 is negative 1. And sine 0 is 0. So cosine 0 is equal to 1. So we got this pattern. Now let's substitute it. So let's transfer to another page for substituting the values of the function. So by continuing, we get the cosine x is equal to, so the value for f sub 0, f function 0 is 1 plus 0 plus, okay, we get negative, so it should be negative 1. So it will become negative x squared over 2 plus then 0, then again x raised to 4 over 24. So that is the equation and so on. So we get 1 minus x squared over 2 plus x raised to 4 over 24, and so on, since it is a continuous function. So we get the second equations that we form. So we get the equation for cosine x, which is 1 minus x squared over 2 plus x raised to 4 over 24. So let's get the third equation, which is I times sine x. So let's compute first for the value of sine x, which is sine x is also equal to the Maclaurin series because it is a continuous function also. So we use this formula again. So let's write it again. Then by this time, our function is sine x. So let's continue our writing the Maclaurin series. Then let's get the derivative or the function x is equals to sine x. So the first derivative of our function x is cosine x, and the second derivative of our function x is equal to negative sine x because it is the derivative of cosine x. Then the third derivative of our function x, which is negative sine x, is negative cosine x. And the fourth derivative of our function x, which is negative cosine x, is equal to sine x. So now let's get the value of f of 0. So sine x is equal to sine 0 is equal to 0. Then cosine 0 is equal to 1. So we get this pattern. So let's substitute 0 to x. So we get this pattern. So by knowing this pattern, we just simply substitute it on another page. Let's substitute it to our Maclaurin series for sine x. So what we get on this equation, so 0, since f 0 is 0. So let's just simply write this. So we get the function as x minus x cubed over 6 plus so on. So this, but based on the equation, we need to find I sine x. So right here, so we need to find I sine x. So just simply multiply I, the equation. So we get ix minus ix cubed over 6 plus so on and so on. So we get the third equations that we need to know. So we get I sine x is equal to ix minus ix cubed over 6. And by looking for the equations that we formed, we notice that if we add cosine x plus I sine x, we form this equation, 1 minus x squared over 2 plus x raised to 4 over 24, and the value of I sine x, which is ix minus ix cubed over 6. Then let's rewrite it according to the degree. So we get 1 plus ix minus x squared over 2 minus ix cubed over 6 plus x raised to 4 20 over 24. So what we notice is that cos it is also equal to e raised to ix. So what we mean, or what we notice here, is e I raised to x is equal to cosine x plus I sine x, right? So but based on Euler's identity, x should be in pi. So let's substitute cosine pi plus I sine pi to x. So we get this equation. Cosine pi is equal to negative 1 and sine pi is equal to 0. So we get this beautiful equation, right?